Have you ever stopped to think about how the power coming out of your wall, which is, let's be honest, kind of chaotic, gets transformed into the steady, reliable juice that actually powers your phone? Well, today we're going to tell that story. It's about a super clever solution that basically makes our entire digital world possible. It's the story of the rectifier.
I mean, think about it for a second. Your phone, your laptop, even your Wi-Fi router. Pretty much everything has that clunky power brick, right? Why is that? Why can't we just plug these things straight into the wall? Well, the answer to that question is exactly where our story kicks off. So here's the fundamental problem. The power grid delivers what's called alternating current, or AC. You can see it here. It's constantly flipping back and forth. But all our sensitive electronics, they need direct current, or DC, a nice, smooth, one-way flow of electricity. If you tried to pump raw AC into your phone, well, you'd basically have a very expensive paperweight. So we need some kind of translator between these two different power types. And that, my friends, brings us to the hero of today's story, the rectifier. It's a device with one critical job: to take that wild, untamed AC from the wall and convert it into the calm, predictable DC that our gadgets desperately need. But how in the world does it do that? Okay, so to build a rectifier, you need a very specific tool. Think of it like a super strict bouncer at a club, but for electricity. It's called a PN junction diode. Now, that sounds technical, but all it really is a one-way gate for current. The whole idea is actually beautifully simple. A diode is basically an electronic check valve. It lets the current flow through in one direction, no problem. But if that current tries to turn around and flow backward, nope, the door slams shut, it's a one-way street, and that simple fact is the key to everything we're about to do. In engineering speak, we call these two states forward bias and reverse bias. When the voltage is pushing the right way, that's forward bias, the gate is open and current flows. But when the voltage flips and tries to push the wrong way, that's reverse bias. The gate closes and the current gets blocked. It's this simple open and shut case that we're going to exploit to tame AC power. All right, so we've got our one-way gate. What's the easiest, most straightforward rectifier we can possibly build with it? Well, the first attempt is something called the half-wave rectifier. It's a decent first try, but as you're about to see, it's got a major, major flaw. So here's the circuit. It couldn't be simpler. You just take your AC input, you stick a single diode right in the path, and you connect that to your load, whatever you're trying to power. Now, when the AC wave is in its positive phase, the diode says, come on through, and lets the current flow. But what do you think happens when the wave swings negative? Exactly. The diode slams the gate shut and blocks the current completely. And this graph shows the result perfectly. I mean, sure, we've got a kind of pulsating DC, which is a start. But look at those huge gaps. We've literally just chopped off the entire negative half of the AC wave and thrown it away. The source material really puts it bluntly. It says the negative half cycle is just blocked or lost. It's pure waste. All that energy that the power company sent to your house, poof, gone. That just can't be the best we can do. And here's the number that really hurts. The absolute maximum, best case scenario efficiency of a half-wave rectifier is a pathetic 40.6%. That's like ordering a pizza and throwing more than half of it straight into the garbage. It's just so inefficient. Oh, absolutely we can do better. This terrible inefficiency created a massive need for a smarter, more clever design, a way to not just block the negative half of the wave, but to actually use it. And that brings us to the true hero of our story, the full-wave rectifier. This is the ingenious design that finally solves the problem of all that wasted power. And this is it, the full-wave bridge rectifier. Now you can see instead of one diode, we're using 4, and they're arranged in this special diamond shape. This isn't just about adding more parts for the sake of it. This entire arrangement is a totally different strategy. It's specifically designed to capture both halves of that AC wave. Okay, so here's where the magic happens. During the positive part of the AC wave, 2 of the diodes switch on and steer the current to our device. But then, during the negative part, instead of just blocking it, the other 2 diodes switch on. And they pull off this incredible trick. They redirect that negative current so that it flows through the device in the exact same direction as the positive current did. It effectively takes the negative half of the wave and flips it upside down, making it positive. And would you look at the result? It's beautiful. Check out this output waveform. No more gaps. We grabbed the positive half cycle, and then we flipped and grabbed the negative half cycle. We now have this continuous stream of positive pulses.
So it definitely looks a lot better, but how much better is it really? Come on, let's put the numbers head to head and see just how big of a win this is. Okay, this comparison table tells you everything you need to know. Yeah, okay, we're using 4 diodes instead of just 1, but look at the trade-off. The maximum efficiency jumps from that sad 40.6% all the way up to 81.2%. It's literally twice as efficient. And then there's this ripple factor. That's just a way of measuring how bumpy the DC is. Lower is better. The half wave is a really bumpy 1.211, but the full wave cuts that down by more than half, to just 0.482.
So the conclusion is obvious, right? We get twice the power out for the same power in, and the quality of that DC power is way, way smoother. It is a total, undeniable win for the full wave design. But our story isn't quite over yet. Even with our hero's big win, the job still isn't 100% perfect. As the source material correctly points out, this output still isn't that pure, flat line of DC we're looking for. It still has these little humps, these leftovers from the AC wave, and we call those ripples. And for really sensitive electronics, even those little bumps are a problem. So to get from this pulsating DC to the perfectly flat DC that our devices crave, we need to add one more step. After our rectifier does its job, the signal goes to a filter. And the filter's only job is to take that bumpy output and smooth it all out.
And that's where we're going to leave it for today. We've solved the main problem, right? We turned that chaotic AC into a nonstop, pulsating DC. But that final step, smoothing out those last few bumps to get it perfect, well, that requires a whole new set of tricks. We'll dive into all of that in our next explainer. Thanks for tuning in.